It's my pleasure to introduce Professor Roy Maartens, who is Associate Chair at UWC, and he's going to be talking about cosmology with the SKA. So over to you, Prof. Maartens.
Thank you. I'd like to start by just congratulating the SAAO on its 200th anniversary. It's really a marvelous achievement. Quite fantastic to think of this in Africa. And I'd also like to thank the organizers of this historic symposium. I'm going to talk to you briefly about cosmology with the square kilometer array, which is the part of it which is located here in South Africa. Now, this morning's session had a very interesting talk by Bernie Vanneroff entitled The Golden Age of Astronomy in South Africa. This is an appropriate moment to reflect on that at SAAO 200. And Bernie gave details about this golden age, but it's basically rests on the two major facilities that we have here in South Africa. On the one hand, we have SALT managed by SAAO, and on the other hand, Meerkat and the which will become part of the SKA mid-array, managed by SUREO. They have some common science areas, such as transients, things that go bang in the sky, and the study of galaxies. But what will be delivered by the SKA and partly by Meerkat is new advances in cosmology, giving great opportunities to us here in South Africa, which we could call part of the golden age that Bernie was talking about. So if we take a quick look at cosmology that is coming with the next generation of galaxy surveys, the SKA is definitely there amongst them, and I've just chosen two others as examples, the Euclid Space-Based Telescope and the LSST, now known as the Rubin Observatory, based in Chile. This next generation of surveys will map the matter distribution across huge areas of the sky and out to high redshifts. One of the things that the surveys will do is to do what current surveys do much better. In other words, essentially they will probe the dark sector to unprecedented precision. This means the dark matter which builds and stabilizes galaxies, but whose nature is still unknown, together with the dark energy, the field that is thought to be driving the accelerating expansion of the universe. But in addition to those standard dark sector cosmology goals, these new surveys that are coming up, the SKA being one of them, will allow us to do certain new things in cosmology. In particular, I will briefly describe two of them, probing the primordial or very early universe, just straight after its birth, and probing the large-scale geometry of the universe. So how do galaxy surveys probe the entire universe, the universe on the largest scales? First of all, you need millions and even billions of galaxies to get the required statistical power to do this effectively. But once you've got that, by measuring the positions in the sky and the shapes of galaxies sometimes in huge volumes of the universe, we can achieve these basic goals. First of all, we can test the models of dark matter and dark energy to very high precision. And the more galaxies we have, the more measurements we have, the better we can do this. And secondly, we can uncover imprints from the primordial universe, faint as they are. I'll come to that later. And finally, we can probe the geometry or the shape of the large-scale universe. So it's all based on having lots of galaxies distributed widely across the universe in space and time, and being able to measure essentially their positions and, in addition, their shapes if we want extra information. So SKA cosmological surveys are based on the 21 centimeter emission line of neutral hydrogen. If you don't know about this, then it's very interesting to discover that neutral hydrogen actually emits radio waves, very weakly, but with a definite wavelength of about 21 centimeters in the rest frame of the hydrogen atom. So this arises due to the spin flip transition. The aligned spins of the electron and the proton are a slightly higher energy state than the anti-aligned spins, and so the flip of spin releases a photon of 21 centimeters. So if we can actually detect this emission line, then we can, at the same time, get a very accurate measure of the redshift of the galaxy that contains the neutral hydrogen. So this is the basic idea for cosmology with the SKA, based on the 21 centimeter line. If we look at this cartoon, which summarizes the history of the universe, time goes from left to right. And on the left is the beginning, the Big Bang, the start of the universe. The universe starts off as extremely hot plasma. And once it's cooled enough for protons to combine with electrons to form the first atoms, the hydrogen atoms, after about 400,000 years, we have the cosmic microwave background temperature anisotropies imprinted on the sky, which we see through the Planck satellite. But after that moment, the universe, in terms of normal matter, is dominated by neutral hydrogen in what's known as the dark ages, because there are no stars, they have not yet formed, and of course no galaxies. And during the dark ages, neutral hydrogen is slowly giving birth to stars. And these stars switch on at the cosmic dawn when they first light up the universe, and then they start to ionize the intergalactic medium in the epoch of reionization. If after a few 100 million years or so, the intergalactic medium is completely ionized, and the remaining neutral hydrogen in the universe is trapped in galaxies. So the epoch of reionization is part of cosmology that'll be studied by the SKA low instrument, which is located in Australia. And I'll be talking about the SKA mid-frequency instrument here in South Africa, which will look at post-reionization galaxy surveys. So if we consider an SKA galaxy redshift survey with a 21 centimeter line in phase 1 of the SKA, we discover, unfortunately, that this will not be a game-changing survey such as those with Euclid, for example. We will only be able to cover 5,000 square degrees of the sky out to a redshift of about a half, not very high. And the reason for this is that it's very hard to detect the 21 centimeter line, which is extremely weak, especially at cosmological redshifts. But as you can see from this diagram here, where the blue points correspond to the errors on the Hubble parameter that could be measured by SKA galaxy survey, and the black points show the much smaller errors achievable with Euclid, for example. This survey, although it won't be competitive with Euclid, it will fill a gap which is very useful as a complement to other galaxy surveys. So one might be led to believe then that cosmology with SKA in phase 1 is not really possible. But this is actually not the case. And the point here is that it is not essential for cosmology to resolve individual galaxies. We can actually just add up the entire 21 centimeter emission in each pixel in a field on the sky. And it's shown in the cartoon here. On the left is the individual galaxies which we're not able to resolve, so this is just a simulation because it takes too long. But on the right is the intensity map, which is a blurred image of the left. And you can already see the patterns on the right which underlie the patterns that come from the galaxies on the left. So provided the blurring is not too bad, this can be very useful for cosmology. This is known then as H1 intensity mapping. And SKA in phase 1 can do a very effective intensity mapping survey over about 20,000 square degrees of the sky out to a redshift of 3, which is a huge volume of the universe. So let me then move on to how this intensity mapping survey delivered by the SKA can probe the primordial universe. I show here another cartoon of the universe again with time going from left to right, starting with the birth of the universe. And in fact, almost straight after the birth of the universe, there's a very brief but very high energy period of a super fast acceleration of the universe known as inflation. And that really is the primordial era I'm talking about. And then we see again here the CMB at 400,000 years and the galaxies that we're interested in from about 1 giga-year onwards up until today, 14 giga-years later. So the key thing about inflation for the purpose of cosmology in this talk is that quantum fluctuations are generated during the period of inflation. These fluctuations are Gaussian for the simple models of inflation, but there are many models of inflation which generate non-Gaussian fluctuations. And so the level of primordial non-Gaussianity, which is measured by a parameter called FNL, can be a powerful probe of inflation. For example, if FNL is less than about 1, this will rule out very many multi-field models of inflation. Well, why are we interested in these quantum fluctuations? It turns out that these fluctuations are precisely the things that seed the growth of the large-scale structure. They are responsible for the patterns of the cosmic microwave background temperature anisotropies and for the distribution pattern of the galaxies. In other words, primordial non-Gaussianity leaves a trace in the CMB and in galaxy surveys. So if I go back to that cartoon, I've now added the FNL, which is generated in the primordial universe by inflationary quantum fluctuations. It is frozen and then can be measured by mapping the cosmic microwave background at 400,000 years, and it remains frozen in the galaxy distribution when it can be measured by galaxy surveys that map that distribution. The state-of-the-art constraint on FNL comes from the Planck telescope using the CMB. And the measurement is that it's 0.8 plus or minus 5. So the error is quite large. The 1 sigma error on FNL is 5. It turns out that the future CMB experiments won't really be able to improve much on this. And so we have to rely on galaxy surveys to probe errors on FNL below the threshold of 1 that allows us to discriminate a lot of models in the early universe. The galaxy distribution, as I mentioned, carries a fossil signal from the primordial universe. It's quite remarkable that imprinted in the pattern of galaxies, but very weakly, is this message from the very early, very first moments of the universe. And in order to amplify this signal, we really need to combine galaxy surveys, even with the next generation surveys. Then what happens if we do this? If we consider the synergy, the combination of SKA1 intensity mapping survey with LSST and with Euclid, we find by doing forecasts that with Euclid we can reach an error of just over 1, which is nearly there. But with LSST, which is a larger survey, we can go below 1. And so we will have remarkable constraining power to give us information about the very first moments of the universe. And this is something we'll be able to do with the SKA located here in South Africa. Can we do anything before the next generation surveys are all taking data and active? Well, it turns out that MeerKAT, if we combine MeerKAT with DES, the dark energy survey, the premier survey going on at the moment, then we can indeed be competitive with Planck. The diagram here along the y-axis is the error on FNL, and along the x-axis is the sky area of the combined surveys. We see that from the green curve, DES on its own is not competitive with Planck. At best, it gets an error of about 10 or 11. But if we combine it with MeerKAT, especially in the high redshift band of MeerKAT, the red curve, we see that we're competitive with Planck even with a sky area as small as 2,000 square degrees. So this would be quite remarkable. That could be done before any of the next generation surveys are active. And my final topic, as promised at the beginning, is how do we test the geometry of the universe with the SKA? First of all, what do I mean by that? It's a well-known fact that we are moving relative to the cosmic microwave background. And this motion of ours relative to the rest frame of the CMB generates a dipole in the CMB temperature. in the direction of our motion, our relative motion, the temperature is higher, and in the opposite direction it's lower, and there's a variation in between those extremes. Now, the universe in the standard understanding is assumed to be spherically symmetrical, isotropic about us on average. This comes from the cosmological principle. And it requires that the dipole velocity measured in galaxies is equal to the dipole velocity measured from the CMB. This is a critical test of the standard geometry of cosmology, and it was formulated by George Ellis from UCT and Baldwin in 1984. Current surveys, there are two current surveys which have a large enough sky area to attempt this test. The one is the NVSS survey on the JVLA, the American Radio Telescope, and the other is the TGSS survey on the GMRT in India, the Indian Radio Telescope Array. But it turns out that although we can measure the dipole in both of these surveys, the errors are too large for us to apply a test of the cosmological principle. But if we look at an SKA1 radio continuum survey and we simulate the dipole that will be achievable in such a survey, shown in this diagram here with sensitivity in decreasing from top left to bottom right, even in the low sensitivity case, we find that we would have enough constraining power to measure the dipole at about 10%. And this gives a possibility that we can have the first robust test of the cosmological principle, the test of the geometry of the universe. And I'll stop there. Thank you very much.
Well, thank you very much for a fantastic talk, Prof. Maartens. I have a question. So you mentioned that Meerkat combined with DES would be enough to would have great sensitivity. Well, so what typical sensitivity would you need over the entire footprint to be competitive?
So let me just go back to the diagram. So the key thing that we would need here is the sky area and the time. The amount of time you can spend on sky and the area of the sky that you can cover. Those are the two key ingredients. I didn't mention the time here, but it's a few thousand hours would deliver this. If you have less time on sky, then effectively you have less sensitivity in some sense. I think that's the way to answer your question. So if we have enough time and enough sky area, then Meerkat as it is forecast to be able to compete with Planck when combined with DES. But if we reduce the time and reduce the sky area, then the measurement gets less precise.
Okay, thanks.
I also have a question. I was just wondering, I mean, it's exciting to think about what SKA is going to bring to the table, but has there been any exciting cosmological results from Meerkat while we are waiting for SKA?
No, and the reason for that is that Meerkat was not designed as a cosmological instrument. In fact, the SKA in phase one was not specifically designed for cosmology either, but the SKA is more suited to cosmology than Meerkat. Nevertheless, Meerkat is able to do cosmology. And there are some of us back in 2017, as a slide which I didn't use, led by Mario Santos, proposed a cosmological survey on Meerkat called MEERKLAS, the Meerkat Large Area Synoptic Survey, which would include cosmology as its main goal. So this is something that will be proposed for Meerkat, but at the moment Meerkat is doing other large survey projects. None of them is yet cosmological.
Okay, thank you very much. Thank you for a great talk.